This heatsink model illustrates how complex 3D geometries can be constructed from simple shapes. We'll start with the base block and circular fins created through solid extrusion, then model the inlet and outlet pipes using solid revolution, and finally generate the curved coolant channel with a solid sweep. By the end, we have created a complete 3D assembly in ABAQUS CAE that mirrors this real-world cooling system. If you're interested in this video, let's sit back and relax as we get started with the video. I will encourage you, before you dive into this video, to look at this video which I made about using ABAQUS CAE to create 2D parts. That will be a good foundation for you to start with before you go on to the 3D framework that we're looking at in this video. So within ABAQUS CAE, there are 3 ways to create an ABAQUS 3D part. And what I've got here are 3 methods. The first is the extrusion method, followed by the solid revolution, and finally the solid sweeping method. And I want to unpack them individually so that we can understand what's really happening with that. So the first one is extrusion. So got a 2D sketch which is a cross section, and it's normally pushed or pulled. So you pushed it to create an outward, or pulling, to create an entry, a re-entrant. So you either push or pull along a straight path to create a volume. This is unique. Extrusion is usually extruded along a straight path, and then that leads to a volume. So if we look at the mathematics of what is really happening here, so let's say we define a profile that lies in the XY plane as a 2D system. What extrusion does is that it extends that 2D plane into a 3D geometry along the z-axis by a distance L. So mathematically, what we're trying to do in creating a volume is we're starting off with an area of a 2D geometry in the XY plane, and we're multiplying it by the length, and that creates the volumetric space that we're interested in. That's essentially what it is. So usually when you start creating extrusion within ABAQUS CAE, what you will need to do is to sketch the 2D domain first, which defines this area as a function of x and y, and then the extrusion process will lead you to creating the length. So you can change the length even after you've created the first model. So let's consider what we're doing to sketch the principle. So this is a 2D domain, a circular geometry of area AX, and we want to extrude it by a distance of L. So if we do that, so you can see this is the extrusion process. So it starts off with that base geometry, extrude it to get to this length L. So we can then change L depending on what length of extrusion we want. We can also reverse this process by maybe starting off with a geometry like that, create something there and extrude, pull it in, extrude inwards to create a gap. So it's not always about building, you can also subtract. But that whole process is you always start with a domain and you extrude it inwards to create the gap of interest. And that therefore leads us to defining a final volume in the XYZ Cartesian plane, and so this becomes extrusion. So that's the first. So the second method is solid revolution. So what does that mean? So again, a 3D solid is generated no more by a linear extrusion but by rotating a 2D sketch about an axis of revolution. That's what revolution method is. So again, what is mathematics that's driving this? Again, we have a profile in 2D that lies on the RZ plane. So an RZ plane, then when you revolve the solid about the z-axis through an angle theta, you get the volume. So we could say in this case, basically the volume in terms of RZ theta, which is this polar coordinate system, what we'll end up with, the A RZ being the geometry of the plane that we've created in 2D, rotated about the z-axis through an angle theta. So you can see all the variables that are required in order to create a 3D space using geometry, using solid revolution. So let's try and visualize that. So the first thing you need to do when you get into ABAQUS to create this revolution is that you need to define a reference frame. So within ABAQUS, this is already preset. So once you activate revolution, there is a reference frame which is the axis of rotation, and this axis of rotation will normally be a certain x or y axis, but in this case I'm using the r and z axis because we are in polar coordinate system. So what we have here is that the radial axis, and then there's also the axis of revolution, which is the z-axis. And so the geometry that we're going to create in this case is a rectangular geometry that has an area of ARZ. So this is a 2D geometry that we are creating. We sketch it on this plane. So once you get into ABAQUS, you sketch this domain on this plane, and then the next thing you need to then do is to go on to rotate it by an angle theta. That angle theta usually is between 0 and 360 degrees. It will never be 0 because then you don't have any volumetric element at all. It will just be that 2D element. But it can be 1 degree, it can be 360, 359. So anything within that range, or even 360 if you want a complete close-up of the domain. So this is what we have in terms of how the angle could vary. So it really depends on what you want to do in your simulation, and I will illustrate that in a moment when we get into the modeling. And then the next thing we now have to have is that rotation about the axis. So imagine this space, you need to rotate it 360 degrees to create that base. So that forms the base of the new geometry, similar to what we did with extrusion. You've got the base, but as well, because it's an RZ reference frame geometry, you also need to rotate. While that rotation is happening, it's also happening longitudinally around the Z axis. So in effect, this becomes the geometry that we have. So and that's what the solid revolution looks like. And in purposely, I have allowed this sharp cut in the center to exist because I wanted to illustrate really what is happening. The fact that you can have a central core that is exposed in this system, and that's how this actually works. So in the end, what we have will be a volume in polar coordinate system, which is RZ and theta, but I'm saying it's equivalent to also the volume in terms of X, Y, Z. And this is because there's a predefined Cartesian reference frame in ABAQUS that everything is defined in X, Y, Z coordinates. So even though the principle of its generation is in polar coordinates philosophy, however, we can still treat that volume because they're equivalent. That volume is equal in XYZ coordinate system. So it's okay to start treating our volume in this XY coordinate system. So the third approach is called the solid sweep, and it's actually one of the most general and most powerful of the 3D creation geometry, because the other two tend to have almost a linear approach to what you're doing. Either you extrude along a length or you extrude about a defined angle. What if the path of extrusion is a bit convoluted, a bit complicated, like you're trying to model a helical loop? So how are you going to do that? And so the solid sweeping approach is a really powerful approach. So the principle within the solid sweep is that you define a profile sketch. So again, a 2D sketch is then defined, and then it's swept along a predefined path that is not, can be linear, can be non-linear, could be whatever you want. So this is why I say it can be linear, it can be curved, but there's this flexibility of having some really excellent path that you are defining. So mathematically, if a profile lies in the RZ plane like we did before, and exists also a path along a normal vector, so we need to find a path of which the outward acting direction of that path is a normal vector. So we can sweep that particular shape along that normal vector to therefore create the whole volume. So what does that mean? Again, the volume you're creating will be the volume in terms of RZ and T being the outward normal acting direction. So we've got our RZ axis swept along the path T. So what does that look like? So we've got a profile again, a 2D profile. It's in this RZ plane. So similar plane like what we did with the revolution method. And then a defined area. So you already know what the area, which is the base of that geometry. And then we now need to define a path. So that path could be any random path. So I've sort of used a nonlinear path in this case, where the outward acting normal is tracking every point along this path. And then at the end, what you're going to do is extrude this base or sweep this base in this way to now create the geometry that we're interested in. So if we do that again, you extrude that base to create the geometry that we're looking at. So you could see now we have some really interesting geometry that is non-linear, that is really interesting, and we can do some really amazing shapes using this solid sweeping approach. So our volume is also equivalent to the volume we generated in terms of XYZ coordinate system. So if we just sum up what we have done here, so there are three ways of creating a geometry in 3D domain in ABAQUS. The first one is extrusion, the second one is solid revolution, and the third one is the solid sweep. And that's what we are going to demonstrate this in this video. I want to use an example problem to illustrate what is going on here. And so this problem is the 3D modeling of a nanofluid-cooled pin fin heatsink in ABAQUS CAE. Don't worry if you don't know what this is. So this is basically a heatsink that is useful in managing heat within some electronic components. It's published in a paper here. So this is a paper that I took that geometry from. So it was in 2019. This paper was published by Ambrim and colleagues in South Korea. And it's really interesting. So I'll put a link to this paper in the description section of this video if you're interested in seeing that. So it talks about the physical model, the formulation of that. But the thing I really want you to have a look at is this geometry. So this is what we are going to use. I've made some adaptations to this, in order to give us a feasibility to create all the geometries, all the 3D parts that we have in mind. But I thought this was a complicated enough problem to use to illustrate what is going on in this. So the scenario we're going to work on says that a microfin heatsink is designed for cooling high performance electronic components. Now the heatsink base is made from aluminum and contains circular fins, and then also it has an inlet and outlet pipe and a curved return channel that recirculates the coolant fluids during the operation. Now this coolant flows through the inlet pipe, circulates through the internal curved panel, passes through the circular fins and enhanced convective heat transfer, and then exits through the outlet pipe. The coolant can be water, it can be a nanofluid mixture like the guys talked about in the paper, aluminum oxide and water. So I put a reference to that paper, which is where I'm taking the inspiration for this. So in terms of what we're trying to do with this video, our ABAQUS CAE objective really is to design the 3D parts that is representative of this. And that will include the heatsink base, the circular fins, the inlet and outlet pipes, and the curved return channel. So we've got the heat sink base. So this is one solid base, and within that it's made of the same material as this aluminum fins. So I call it a sub part 1. So I basically create that. There's also a sub part 2, which is the fin, which will be created using an extruding operation. So they are both extrusion, slightly different ways of doing them, but they are basically extrusion in what we're trying to do. Whilst for this one you have to create and push. For this one you have to create and pull up, but I will illustrate that when we get into ABAQUS. The third thing are these inlet and outlet pipes, and I want to use a solid revolution approach to create them. And then the final one is this really interesting coolant chamber for recirculating the fluid. So again, it's quite curved part, very interesting part, and I'm going to create that using the third method, which is a solid sweeping approach. So these are the 3 components that we have, and we're now going to get into ABAQUS so that I can illustrate how you do all of that. In the next video, I will show you how this is constructed inside ABAQUS. If you've not subscribed to this channel, please subscribe so that when contents like this are made, you'll be the first to see it. Thank you, and see you in the next video. Bye bye.